Hello, everyone. In this video, we will go through Abaqus tutorial, show you how to use Abaqus to do dynamic analysis of a building frame, as you can see here on the screen. Um, as you can see here, this is a building frame with 3 stories, right? 1, 2, 3, and we have some forces applied as a pressure on top of it, and we have so to simulate the load from the construction material as well as the occupants. Then we have some, so those are constant values, and there are also some wind load applied to the left side and the right side. On the right side, the wind load is pretty much constant, while on the right side, on left side, those are we have the increasingly and applied load from 0 to 10 kips at different levels. So now let's say what would happen for this building. So what would be the displacements, especially on the top floor over here, to an Abaqus analysis here. So yeah, so that's the brief introduction to the problem statement over here. Now let's say how we can create the model. Creating the model would be easy, correct? So we create a geometry. We have different beam information over here, and we have the density. I have that density and the modulus of elasticity here. So here we open Abaqus and we change the folder to tutorial 7. This is our work directory. First step, we create we can start create the 2-dimensional deformable wires. So we have everything is in. If it would be better to use inches here. So everything here is inches. So we have the width is 360 inches and the height is 120 inch. Probably it's better to approximate that 400 with that. So the first story we have 360 and 120. 360 and node 1. That's 120. And we go 360 and 120. And we go down to 360, the 1 plus 360, 0. So this is the first story. 360. And, okay, so it's about 301. So this is the first story. And then since the other 2 stories are pretty the same, we can just copy everything. We can do the linear pattern. We'll select everything here. So we go up direction 2. Direction 1, we have 1. Direction 2, and the spacing is 120. And number 3. So this is the geometry here. So we think that's all. The geometry, we save the model here. So you may have a different approach since this geometry is pretty straightforward. So then we define, we go to the property. So we use the same material, modulus of elasticity, and here, the density here. We define material elasticity, and the modulus of elasticity, that's 30. Poisson's ratio, since we will use beam element, which does not require any specific number for Poisson ratio, we can assume 1.2 or 0.3, it doesn't matter here. And then we have the density. Density is 0.00073. 0.0073 is the density of the elasticity and the density here. And then we are also required to input some damping. So for the damping, we have the alpha 3 beta 0.001 and 3 beta 0.001. That's correct. Okay. So those are the alpha and the beta values. Click OK. So we have already defined the material. And let's take a look at here. So we define the damping density and the elasticity, all of them associated with material number 1. So next step, we create the section because we had 3 sections here. 3 sections here. We define that's a beam section. We will use beam section 1 will be assigned to element 1 and line. So we just use a beam 1 line profile. So we will use the profile will be generalized. Just click the generalized. We put the aerial here is 13 and 250. 13 and 250. I12 doesn't matter and I22 doesn't matter. This 2D we can input some smaller number here. Can use the same. Okay. Okay, we need to change pro. So we have used profile 1 centroid and damping. Since we use generalized, it looks like we cannot associate with any damping here. Anyway, we can go ahead put the Young's modulus here too, or just input the material number. So we use the material name, material. We have everything over here. The material have already assigned the damping. Click OK. This is beam number 1, and we have beam 2378. Beam 2378. The same different profile. And the area equal to 6 and 100. 6, 100. It's the same numbers. Okay. And then we have the last one. That's beam 456. 456. Okay. Nice. And the area equal to 14 and 800. 100. That doesn't matter. Okay. Profile before profile 3. Let's use the material type here. Let's check the beam. Okay, so this is the profile 3. And then we have this should be profile 2. Before profile 2. There's material number 1. Same material. Okay, we have already defined all the beams, and then we assign the sections. We assign the, so basically 1 and 9, that's the first floor, and the second floor, and the beams. We assign first floors, we will use the beam 1 and 9, and second and third. So you can press Shift to do multiple selections here. So that's beam 2, 3, 8, 9, and then we define the 4, 5, 6. So we have different beams here. And so we save the model. Okay, so as long as we are done here, for beams, please make sure you also assign the beam orientation here. So we select all the beams to make sure the beam is aligned. We have the beam orientations here. So for two-dimensional problem, that's not an issue because you can just use the default one. So yeah, we have the direction 1 and 2 corresponds to the direction, and whether which has a larger or smaller moment of inertia. For our case, we have everything is the same, so that doesn't matter here. We just click OK. We're done with this step. We just click OK. So then we go to assembly. Assemble the independent, and I can do independent. Then we go to steps. Steps here is important. Here we create, that's not static anymore. So we will go at dynamic and implicit. Dynamic node. So here we need to input how many set the time step, and so here so firstly we will try use the time step 1, that's a static load. We apply all the static load. Secondly, we create a dynamic load here. We use 0.002, we use like 4 seconds. We use the time 3. So that's why we need to create a static firstly. So just use time period as 1 here. Just click OK, nothing to change on here. So we make step 2, that's dynamic node, implicit. And then we have increment time period, we change that to 3. We have number of increments, we use the number of increments 2000, and then we use 0.002, 2000, 0.002. Yeah. So that's a time step, 0.002 seconds, and we use 2000. So that means in total we consider 4 seconds. And we divided the 4 seconds to 2000 steps. And we use the end of the time is 3, and that doesn't matter here. Okay, we click OK. So then we apply the load because we have the constant load, 50, 100, and 100 over here, and we need to multiply that by 25 to get the linear node here, and divided by 12 to get the node in pound per inches. So I have already calculated that in my node here. So the top one is 104,208, and yeah, the first and the second floor are larger, and the roof is smaller. And then we also have some constant on the right side, 31.252. Okay, so that's how we apply the load. We have node directly, and then apply the load. We have the firstly the pressure, the linear, the line node. Have the line node. So we have the first floor, and the roof is smaller. We have the uniform, that's 104.17. 104.17. That's linear node. And then we have this two linear node, and double that's 208.33. That's 208.33. So those are the vertical load. And we have some pressure on the right side too. So those are the 9 node, that's 31.25. 31.25, 9 node. So we have select this one, this one, this one. That's 31.25 to the right, with all that line. So all the forces are static load, constantly, because we don't care about the initial vibration here. So then we apply the nav load, so the dynamic load. Oh, looks like, okay, so all those needs to be in step 1, sorry. Step 1, there is no way to change that. Left, okay, move left, and then we move left. So they are dead load, they're dead load. And they will be there permanently, right? Okay, so then we apply the increasing node here, and that load is increasing from 0 to 10 kips. So here we'd better to convert everything in pounds, because here everything is in pounds. And yeah, so that's 10,000 pounds. We need to define how the node varies. So we need firstly that's the concentrated force from node 4. So create. So the first one. Okay, so that's a variation. So we need to define amplitude. Define amplitude. That's a tabular node. Application. Just use the same one. So that time when times 0, amplitude is 0. When times 0.3, that's 10,000. 10,000. And we may use more here, because if we want consider more, point that we have. We will consider 4 seconds, so probably we better to input more. So 4 seconds. So for all the 4 seconds, it's constant to 0. We use the amplitude here, so that the first floor on the roof, that's smaller, that's 0.5. Use the ratio here, 0.5. You see the 0.5, and we add another one. Second floor, let's we go to the CF1 in the X direction, so that's at 0.8. Use the same amplitude, and then we apply 1.0 here. Amplitude here. So now we have all that load applied here. Excuse me. So then we restrain the bottom. Restrain the bottom. So the bottom two nodes will be constrained. The fixed. So that's the boundary conditions. So up to here, we should be able to mesh. So we do the mesh. So we use the element size equal to 1. So we use one element for for all the nodes there between each node. So go to the mesh. We define mesh size. So by number, we would like to use only one here. We select the beam type. Check the so shear flexible or shear non-flexible. That doesn't matter. We can just use that. Let's see what one did we use. We use linear type. Okay, so we will use linear shear flexible one. So that we can check the result here. And then we mesh, do the mesh. So everything is meshed. So we may be able to show that the load levels. We want to show that we have the load levels there. So the load level may be a little bit different from showing in a problem statement, that because how the node number is ordered is depends on how you create the model. We have everything here. We should be able to create the job and let it run. And then create a job. So dynamic and nonlinear off. We create a job length here. So dynamic non-linear off. So this is the job. Now we submit the work here. Okay, so the issue here is I11. Okay, so it looks like we'd better to have a smaller I12 in order to make it work. So we go back to the properties. As you can see here, we need to redefine the profile. So we have the, where do we have the profile? Profile here. We want to make sure the I12 is smaller. Just divide it by 2. So we change all the profile here. It's 50. I12 is half of them. So then let's redo that. Resubmit. Okay, so at least now everything's okay. Oh. A 2 million times. Okay, so looks like something it's wrong, we can check the warning here. Numerical, okay, singularity occurs. Yes. What's going on here? Okay. So that means that's okay, something wrong. Let's say even step one is not finished. Probably the boundary conditions. Let's go back to the boundary conditions to see what happened. Oh, okay. So yeah, we need that step one has a boundary condition too. Got to make that. So we resubmit. Now it's running. We can monitor actually. Okay, step one is done at least. No errors, no warnings, and it's doing good. We have finished almost 1,000. It takes a while since the time step is small here. Okay, it's done. It's done. So now we can visualize the results. And we would like to show that the result at node 7. Node 7, let's say that's the top horizontal direction. Node 7, that's on the right side, right? And reaction force and bending moment in node 1 and 2 times 3. Right? And then let's say that whether we can have any data. So for we would like to have the field output. So we put the element pick from the lab view. So that's the top. Okay. Pick from. I cannot. Okay, position. We just use nodal. And type. We need the displacement, the U1. And then we pick one node. And then we plot. So this is the, you can see here, this is the displacement of node 7 and node 7. Actually show node 8. We can also show the bottom ones. So we go back to this one. We would like to add some ones. First floor and the second floor. Plot. Yeah, so we can show that, as you can see here, initially under dead load, under static load, then there is no vibration, but under dynamic load there are some vibration with including the dampings. The vibration it decays to 0. So those are the displacements. We can also show the forces. We can show the forces. For example, we can uncheck the force. We can show the reaction forces. We would like to show the reaction moment, reaction force, the vertical direction. Let's say check the reaction pick from the view one entity. Okay, plot. So this is the reaction force at node 1. We can add the reaction force at node 2 too. So, and the reaction force, the vertical reaction force is a little bit different from 1 and 2 because that node is different. We can also show the horizontal forces. Horizontal forces. And we can show the horizontal forces. The horizontal forces and the vertical forces, the different magnitudes here. So that's how we interpret the results. We plot the time history to plot the forces as a function of the time so that we can see how the forces and displacement varies for dynamic loading. And you can try the other jobs shown there and I'm going to give you some small assignments there for you to do the other two cases. And if you follow the same procedure here, you should be able to get that work. I think that's all for this video, and good luck to your try. Thank you. Bye-bye.